Okay, so we're going to be continuing on in Module 3 today. So the last time we were together, we got started on Module 3, which was working mostly out of that handout that we had. So if we go back to our learning plan, Module 3, we were able to get through our first PowerPoint presentation, okay? And it referenced the first pages of that velocity handout. So I have it actually printed out underneath here. We got all the way through page 6 the last time that we were together. So we're going to continue on in this handout today, and we're going to be starting on page 7, if you would. Now I am going to pull up our PowerPoint presentation part 2 and kind of start there and then switch over to our handout in just a bit. Okay. So we're going to continue on in chapter 6. We're building on what we learned the last time in velocity analysis. If you recall, the last time we were dealing with really just one link, and as it was either rotating or going in a straight line, like how fast was it going? And we were looking at angular velocity, how it relates to straight line velocity, or V, okay? Now what we're going to do is we're going to work with kinematic mechanisms so that once we identify an input, for instance, maybe there's a motor attached to our input link or our crank, and then it's got a connecting rod and an output or a slider with it, what's happening on the other stuff, okay? So if we know what's going on our crank, now how is that going to affect the things that are downstream, if you would, that they're controlling? So the base equation, the base vector equation for solving straight line velocities on 4-bar mechanisms. Now, these are the V's. So many times, and it depends on the path that particular link is going to take, but we always have at least one or two that are going to be rotating about a center. So they're going to have that straight line velocity component to it. So these are the V's, not the alphas, okay, not the rotationals. So these are the straight lines. So we're going to identify the velocity of something unknown. So that's going to be downstream, like maybe link number 4. We want to know what is the straight line velocity on that. That's going to be equal to the velocity of something that's known. And again, typically that's going to be what's going on my crank, okay? So a lot of times that's going to be kind of the starting point because that's where we know the most information. So the known velocity of something one of the links that we're aware of, everything that's going on. And then we're going to add vectorially to that the straight line velocity of the unknown, which is going to be at the beginning, relative to the known, okay? And then once we get our straight line velocities, we can then use that to potentially solve for what I have here as W, which would be angular velocity on a link that's going to be rotating about a fixed center. So the process that we go through for kind of solving these types of problems are going to be, first, we're going to determine the rotation of any unknown velocities. So what that means is we're going to be looking at the different links and what are the paths that they're going to be taking. Then we're going to determine the direction of any relative velocities that are going to occur. So in terms of if it's a crank, that's going to be the input for a 4-bar mechanism, we want to find out, okay, what's happening on our output. So, looking at what are the directions. So what's the path that it's going to take? And is it either going to be counterclockwise or clockwise? If it's a slider, what is the straight line velocity path that it's going to be taking? Then once we kind of determine, on the picture where things are going or how they're going to move, we want to use the relative velocity equation to draw a vector polygon, okay? We're going to be using what we learned in chapter 3, which was the vector work that we did in module 2. And now we're going to be applying this here to graphically determine any unknown velocities here, okay? And then we're going to determine any unknown magnitudes by measuring those vectors. So we're going to be using AutoCAD to set these up. And we use AutoCAD because it's much more accurate, obviously, than getting out a piece of paper, a scale, a protractor and such. We get our numbers to be like right on, okay? So that'll be kind of fun to see that. So what we're gonna do is we're gonna go to page 7 in our velocity handout, and we're gonna kind of finish up the examples that we see there. So I'm gonna go underneath my camera, and you'll notice that this is the relative velocity portion. So this is page 7 in our handout. Now, at the top here, just kind of redefines relative velocity. Relative velocity is when we need to find the velocity of something unknown that's dependent on or relies on a link like upstream as the input, okay? So for instance, in the 4-bar mechanisms that we've been working with, we have some names for the different links. So first of all, link number 1 is always going to be our frame, which is not going to be moving. Then directly connected to that is going to be what we call our input. Many times this is also referred to as the crank. So it's kind of like the input for what that mechanism is doing. So it could be a manual input where it literally is a crank, a hand crank, a manual crank, or it can be where we attach a motor and it's going to be rotating at the same speed as a motor, which is probably more typical for industrial applications. So this is going to be our crank. Now, as I said earlier, a lot of times, now sometimes we might start at the output and be like, okay, I need this output. So what does my crank need to be? You might work backwards, but most often for the problems we're going to be doing, we're going to know what's happening on our input right here. So this area right here, this right here, I like to call the input, okay? Where that crank is, like what's that doing? So many times we're going to know how many RPMs that's going and in what direction, clockwise or counterclockwise. That's going to be identified by this omega, this lowercase omega, which is like that cursive W. And this is going to be the angular velocity of link number 2. And again, in our previous lecture, we went into detail how angular velocity then is going to be every point on that link is going to be going at the same angular velocity. So any point along link number 2, whether it's close to the center of rotation or all the way out at the very end, has the same angular velocity as that link because they lie on link number 2. Okay, now relating straight line velocity, as we know, any individual point along a rotating link is going to have a straight line velocity component. And we, again, saw that in detail last time. If you need to go back and review that, make sure that you do. But we can determine the straight line velocity, which uses the variable v, of any point along that link. In this case, the furthest point out. Now, the furthest point out is what's then connected to our next link. So we usually want to know what's happening there. So the velocity of B, for instance, because it lies and it is only going to rotate around that fixed center as link number 2 does, is going to be equal to the angular velocity of link number 2 times the distance it is away from its center of rotation. So R2, if we know that number, we can calculate the actual magnitude of the velocity B. Okay. Now, I just want us to remember that whenever we are dealing with angular velocity in and out of this relationship, this equation here, this has to be in radians per second. Those are the units always. So for instance, standard units that are going to be given to us for instance, a motor rotation is going to be a value in RPMs, revolutions per minute. Okay. And with that, we can't use that RPMs in this equation. We need to convert RPMs to radians per second. Again, we did that work the last time that we were together. So if you need to look back on that, or we'll be doing problems where we practice that again. So in and out of this equation, we have to have units of radians per second for our angular velocity. Okay. And then R is going to be that distance. Now, because as this rotates around, we can calculate everything about it. That's easy. But we have a connecting rod then to an output link. So this over here would be considered our output. Okay, in this case, it's an oscillating link. That link number 4 has a fixed center at point D, which means that the path of C is only going to be along that radius. It's only going to be able to move along that radius, okay? So usually what we want to know is, okay, if this is rotating at a certain RPM, what's happening over here? Okay, it's not directly connected, so we can't say it's going at the same RPM. And these different distances that are in here are going to affect that, okay? So we're going to be using the relative velocity equation that we just saw earlier on our PowerPoint, okay? Now, the assumption is here that this would be a known value because it's on our crank, which means that C is going to be unknown, okay? So in our relative velocity equation, we always say the velocity of the unknown, in this case, it's going to be velocity of C, it's going to be equal to the velocity of something that's known. Again, the assumption is we would have full information of what's happening on our crank, okay? And B is on the endpoint of that crank. Plus vectorially, this is going to be the velocity of the unknown, C, relative to the known B. The order is important. So if you put B/C, B relative to C, that's incorrect for this vector equation. You have to do unknown to known. So it has to be C in this case relative to B. Okay. Now, directions. Let's draw the directions of velocity B, C, and B relative to C. Now, something about velocities I like to say is that they're always perpendicular to something, always, okay? As we had learned the last time we were together, the velocity, for instance, the straight line velocity component on a single length is going to be perpendicular to its radius back to the center of rotation, and it's going to be in the direction of the angular velocity, right? So we can see that W2 in this case is going in a clockwise direction. So draw the velocity of B as you would anticipate what the direction would be. So as you're thinking about this, it's going to be going in the direction of rotation and perpendicular back to its center of rotation. So if B is out here, the crank going back to A, that's its radius, okay? So that means that B is going to have a straight line velocity that will be perpendicular to link number 2 in the direction of rotation. And this would be our VB, okay? And I have that little note here. Remember, straight line velocities are always perpendicular to the length that they are on. Let's look at the velocity of C. Now, we're going to have to kind of make a little bit of an assumption. If this is going in a clockwise direction, do you kind of see if you would push this along that this would also, W4 would also be in a clockwise direction? Would you agree at this point in time? Yeah. Okay. Because of that, remember, point C, it's on a rotating link. Its path is along that arc. And since it's on a rotating link, it's going to be perpendicular to the radius back to its center of rotation and in the direction of rotation. Okay, so draw the velocity of C as you would anticipate it to look at point C. I'll give you a couple seconds to do that. So thinking about just what it says down here, remember straight line velocity is going to be perpendicular to the link back to its center of rotation and in the direction of rotation. So we're pretty sure it's going to be going in a clockwise rotation. So velocity of C is going to be perpendicular to that link going, if you would, up and to the right, it looks like. Okay, so we drew the velocities for B and C. Let's now draw the velocity of B relative to C. Now, there isn't a link B relative to C, but I'm going to tell you how we do this one. We draw the line of action, the direction of velocity of of C relative to B. I did that wrong. This should be C relative to B. C relative to B, because C is our unknown. That's important. It's going to be perpendicular to the link connecting points B and C. So that means that it's going to be on a line of action. And I draw it dotted because I don't know if it's going to go up or if it's going to go down. But it's going to be the velocity of C relative to B. So make sure that you draw that on this diagram. Remember, this handout you're going to be handing in as your practice problems, okay? There'll be a little bit of extra work to do for their practice problems, but in this case, this will be handed in. So make sure you're adding these notes because I'll be looking for them. Now, we already drew in our W4. So you'll notice that our relative velocity equation here, now it'll become obvious, and I just wanted to kind of draw this out for right now and add some notes to a crank mechanism, one that we have a crank on the input and then we have an oscillating link on the output. This is then going to be, once we have these items in place and we know their directions, as you can imagine, we're going to be drawing our kinematic diagram in AutoCAD. We're going to be determining these perpendicularities, to the actual diagram. And then we're going to be graphically determining any knowns and unknowns here using that vector equation. Okay, so I'm going to stop here with this diagram just to kind of give us the overalls, and then don't worry, we'll do examples with numbers. All right. So any questions right now for what we have here? So make sure that you have your velocity B, C, and C relative to B sketched in. Make sure you also have W4 drawn in to be going in a clockwise direction and labeled. Okay. All right. Now we're going to turn the page. The other type of mechanism that we see often is a slider crank mechanism. This is a 4-bar mechanism, as we've been seeing, throughout. And you're going to notice here, our frame is going to be the non-moving link. Number 2 is going to be our crank. Number 3 is going to be the connecting rod, and number 4 is going to be the slider. We've seen this arrangement in a number of different things. We've seen it on a sewing machine. We've seen it on a reciprocating saw. We've seen it on just a regular piston in a cylinder bore arrangement, okay? These are 4-bar mechanisms that have a crank on the input. So this would be our input over here. And our slider then is going to be our output, okay? Now, as we look at analyzing this, the first thing we want to do is identify the path for which different points are going to be moving along. So, for instance, we have our link number 2 is rotating in a clockwise direction again, and we know that because our angular velocity W2 is identified here going in a clockwise direction. W2 will never be a straight line velocity because it's angular velocity. So every point along this link is going to be having an angular velocity of whatever W2 is identified as. Now on the end point here of W2, we have, on the end point of link number 2, we have point B. An individual point along that link has straight line velocity, right? Draw what you believe the direction of velocity B would be. Okay. You should be showing a vector perpendicular to link number 2 going in the direction of rotation. So since our direction of rotation is going clockwise, our velocity B, straight line velocity B component, is going to be perpendicular to that link going up and to the right. Now, let's look at velocity of C. C is our output, okay? C is our output. C is a slider. This slider can only move in a straight line direction. And in this case, it's going to be horizontal. So it can only move along this line. So if we are rotating our crank at this point clockwise, you'll notice that that means that the velocity of point C, which is at the center of our slider, has to go to the right. Would you agree with that? Notice this one is not perpendicular to anything. This is along the path that the slider is going to take. It's the difference between an oscillating link and a slider. Slider is constrained to straight line motion. So it is only going to be, in this case, left or right. And because of the rotation of our crank pulling this way, it's going to be coming, towards point A. Okay. Now the last velocity, straight line velocity we need here is going to be the velocity of C relative to B. Go ahead and draw what you believe to be the direction for which the velocity of C relative to B would take. So as we know, velocities, straight line velocities are always going to be perpendicular to something. When we have a relative velocity, it's going to be perpendicular to the line connecting the 2 points that we're interested in. So this is the line connecting C to B. So our V, C relative to B is going to be on a line either up and to the left or down and to the right. We don't know which way it's pointing, but it's going to be perpendicular to link number 3 in this case, which is the line connecting points C and B. Now for this problem as well, if we know everything about our input, right? What's going on over there, we can calculate our output using that relative velocity equation. Okay? That relative velocity equation. So we'll be actively looking at this in our examples. So for this page, make sure you have the velocity of B, the velocity of C relative to B, and the velocity of C sketched on the kinematic diagram that we see there above. Okay. Now, question for you. I'm just gonna kind of see. Why don't we have a W4 in this case? Why don't we have a W4? Why don't we have an angular velocity of 4? Right, so this is not rotating about a fixed center. Our slider is constrained to only have motion going horizontally back and forth or in a straight line. So there is no W4 in this case. When we have links that only rotate about a fixed center, now we have that angular velocity because now this is going to be, oscillating or rotating around. And we want to know what is the rate of that. Okay. All right. Okay. So that was page 8. Any questions on pages 7 and 8, at least right now? Okay. All right. I'm going to be looking for those notes to be in there. So let's do our first example. And we're going to use, I think, slider crank mechanisms are a little, if you would, easier. Actually, I don't know that they're easier, but there's one less step that you have to end up taking. So it's a good one to start with. So we're going to look at page 162. This is problem 620. This is not an assigned problem that you have. This is going to be a practice problem that you are going to be handing in. But the problem itself is found at the end of the chapter on page 162. And the problem statement is here in the second column. And the illustration that we're going to be referencing is directly above here. So it says for the compressor linkage shown above, which is right here, figure 619, we want to use the relative velocity method to graphically determine the linear velocity of the piston as the crank rotates counterclockwise at 1775 RPMs. Okay, 1775 RPMs. So up here is that compressor linkage. Our crank would be right here, connecting rod, and then here's that piston. So go ahead And we're going to draw the kinematic diagram to scale for this, this arrangement. So go ahead and open up your AutoCAD. I've already got my start file set. Mine is drawn in inches here. So it would have been the first one that we did. And I am simply going to, I'm not going to walk through this. So independently, everybody should be drawing their kinematic diagram for problem 620. Make sure that you draw to scale, and you also then add all of your labels. You will be doing a screenshot of this and handing it along in with your practice problems. So, so again, make sure that your labels and everything are readable so that when you do hand it in, we can make sense of what you've got. Also make sure that as we add dimensions and things like that, or use it, that you move things so that if indeed we get some overlap because of dimensions we add, that they're not in the way. You want to make it so everything is nice and readable. Make sure you save this as problem 6_20. Whoopsie. I'll go back under here in case anybody needs to see the illustration. So the center of rotation for what would be link number 2 here is going to be in line with the piston path, if you would. Okay, so make sure that it's in line. How many are done, or how many need extra time to get their diagram going? Just gonna look really quickly over here. I'll pull the chat out. Doesn't look like anybody's responding. So I'm assuming that everybody is good to go right here. Okay. All right. So now what we're gonna do is let's go back to underneath. So we just drew our kinematic diagram, and I just have it kind of sketched here so that we can kind of sketch on here as well. So as we look at this problem, we know the most information over on the right-hand side here, right? And we want to determine what is the velocity of point C, or what is the velocity of our piston, which happens to be point C. So, so over here is our input, and over here is going to be our output. Now, because these are not directly connected, we need to use that relative velocity equation to solve for the velocity at C, okay? So as we stated earlier, if this is a slider, its line of action is going to be horizontal in this case. So we can say that the velocity of C is going to be along that line. Now, looking at the rotation of link number 2, if this is rotating this way, do you see how this is pushing then this over to the left? Do you see that? So our velocity of C, we know, is going to be on a horizontal going to the left, okay? But we don't know its magnitude. We know its direction, but we don't know its magnitude. So velocity of C in this case is unknown. So when we look at our relative velocity equation, this is going to be our unknown. Let's see, I'm going to do UK. UK for unknown. Okay, velocity. Now, for velocity of C though, do you notice that this is a vector? So we need two quantities to fully define it. We need magnitude and we need a direction. Now, it is unknown in magnitude, right? So I'm going to put this little circle here resembling unknown magnitude. And then because it is a slider, I know it's going to be along that horizontal line. So we know part of the direction. We don't know if it's going left or right, but we know the line of action, if you would. Well, we do know it's going to the left because where it's at, but we don't know like how long it is. So we can give a check mark, if you would, or known for direction. So the first little part of this, because each one of these vectors needs two things to fully define it. We don't know magnitude yet. We're actually going to measure that on our vector diagram after we get it put together in AutoCAD, but we do know its direction. Now let's move over to the velocity of B on the other side of the equal sign. So velocity of B is on the input link, right? Velocity of B is on the input link. Go ahead and draw in the direction of what you believe vector B should be doing on that link. So velocity B, we know, is going to be perpendicular to the link it's on. So it's the link it's on that's driving it is link number 2. So it's going to be back to the center of rotation. So that means that it needs to be in the direction of rotation. It's going to be down and to the left and perpendicular to that link. That's going to be the velocity of B. Velocity of B. There we go. Now, because it's on a link that we know its rotational velocity or its angular velocity, we can calculate the magnitude of VB at this point. We know how far away this is 2 inches, right? When you drew it in AutoCAD, we know it's 2 inches away from its center of rotation. And we know how fast that link is rotating. Okay. Now remember, this equation. W, the units are important. We cannot directly put in revolutions per minute. We need to convert W2 to radians per second and then use it in our equation. Okay, so I'm going to say equal to, and we're going to put in 1775. And that's going to be revolutions per minute. Okay. I'm going to do the conversion right here in the equation. So expand out. You can do the conversion on the side if you want to, and then bring the number in. But I thought we'll just put it here because I don't have a ton of room. So I might as well do it all at the same time. Now, in the first section here, we know that 1 revolution is equal to 2 pi radians. So revolutions is going to be canceled here. And then we need to get the minutes into seconds. So we know that 1 minute is equal to 60 seconds. Minutes cancel. Make sure you're canceling the units. Sometimes people will write this out and they don't cancel the units. So then when I'm at the end, I'm like, okay, which ones are the ones? Because now what we've done is we've taken 1750 multiplied by 2 pi, divide by 60, and this is in radians per second at this point, okay? Now, that is W2 converted directly to radians per second right in the problem, okay? Now I'm going to multiply it by its distance from the center of rotation. So from A to B, that was 2 inches, okay? So multiply that out, determine what your value is for velocity of B. You should get a value of 371.76. Did you guys get that? 1775 times 2 times pi divided by 60 times 2. Thank you, Tyler. Now, units. So right now, we have radians per second here times inches. Remember, this is like over 1, right? So what would my units be for a straight line velocity in this case? Inches per second, right? But what happened to the radians? It just disappears. Actually, absolutely. It just disappears. So when we multiply anything by radians, it becomes whatever that value for the units were. They disappear. But if we end up with nothing per second, for instance, or nothing there, and we're on a rotating link, we know that the radians like appeared, right? Okay. So our velocity at B, this right here, this is the magnitude. Oopsie. Magnitude. That's the magnitude of the velocity of B. So now we know magnitude. We just calculated it because we knew everything about that. And that's why I say most often on the crank, we know what's going on because many times it'll say the crank is going at, or it's rotating at, or something like that. And it'll be RPMs. Okay. So down here, we were able then to calculate whatever the magnitude was on anything along that link, however far it would have been. We could have done something in the middle here or closer or whatever, but B was on the end. That's where we needed to know. So we've got the magnitude of B. So now we can look here at B. This is a known value. So it's K for known. And we know its magnitude because we just calculated it in step number 2, right? Do we know its direction? Yeah, we know it's on a line perpendicular to the radius back, right? And in the direction of rotation. So we know both magnitude and direction. So that's why it's known. We were able to calculate its magnitude because we were given the information about the crank. And we also know its direction because of the kinematic diagram. Okay, now we already drew this kinematic diagram already, so we're gonna be able to draw some perpendicular lines so that we can get these nice and accurate, and we'll be able to graphically determine this like right on. All right, and now our last vector is going to be C relative to B. So we're going to go back up here, okay? And C relative to B is going to be on link number 3. And it's not on any one of the endpoints because link number 3 does not have a center of rotation, okay? So really anywhere along this link, it's almost like kind of like oblong-y, kind of moving along, okay? It's going to be one of those intermittents, but at this moment in time, the straight line velocity component is going to be perpendicular to that link, but we don't know if it's going up and to the left or down and to the right. And that's going to be our velocity of C relative to B. So down here, when we look at this is going to be unknown relative to known. So our unknown was C, which is at the beginning of our equation, and then B is our known. Now, magnitude. Do we know the magnitude? No, we don't know the magnitude, so we would put a little circle there. But direction, we do know that it's going to be perpendicular to that link. That's why your kinematic diagrams need to be perfect, okay? Double check them before you start doing the work. Or if you get wrong answers, go back to your original diagram. Take the time to make sure that you have, the radius is right, the angle's right if they're given, and all that kind of stuff. Because that is going to, trip you up in your numbers. So we can say that we do know direction. Now, this is a vector diagram. As we look at the vector diagram, as you know, and as we saw in chapter 3 at the end, the very last examples that we looked at, we could have more than one unknown in our equation. Algebraic equations, we can only have one unknown. But vector equations, we can have 2, okay? The only caveat is those 2 unknowns have to be separated by the equal sign because we can only have one unknown on the left and one unknown on the right. Okay. If we had a third unknown, we're sunk. We can't, go on, but we can have 2. So as you can see here, we do have 2 unknowns. We have the magnitude of velocity of C and the magnitude of velocity of C relative to B. And we also have them separated by the equal sign. So we don't have to do any rearranging or anything here. Okay. And we'll be able to use that method that we saw in chapter 2 to determine the magnitudes of those unknown values. Okay, so that's going to be the work that we do next. So we're going to graphically determine the magnitude now of velocity C. So let's see how we're going to do that, creating this vector diagram. So I'm going to go back to AutoCAD. Now, what I want to do is I am going to put in place my vectors at each one of the points that we see here on our diagram. And we're going to either put in known or unknown or however it works. So first of all, I am going to change my object to a different color. I'm going to do object 2, and I'm going to draw in the velocity of point B. Now, right now, the scale that I'm using is, for instance, the length of link number 2 is 2 inches. Okay. When I look back at the work that I just did, the magnitude of velocity of B is 371.76, okay, inches per second. That would mean that this is going to be much longer and bigger than the scale of my kinematic diagram. So what I'm going to do, instead of drawing this 371, I'm going to move the decimal place 2 places to the left, and I'm going to draw the length of B to be 3.7176 inches long. Does that make sense to everybody? Okay. So when you do your final answer, then you're going to have to move that decimal place back 2 places because your answer needs to be in the correct value and units, the correct magnitude and units. Does that make sense to everybody? Okay. So we are going to then draw our vector. So we are going to draw a line. How do I want to do this? We're going to draw a line, and I'm going to draw a line just from a random place to being perpendicular to link number 2. Is that, no, I think I grabbed it. Hold on. Line. And I'm going to do shift right mouse button. I want to be perpendicular to link number 2. I guess I am. I don't think it is. I think it might have grabbed. Let me do that different one more time. Line. I'm going to go from here. I'm going to zoom in, and I want to be perpendicular to this. Okay, I feel better about that. I think it was grabbing that little radius. So there's my line perpendicular. Then what I'm going to do is I'm going to move it, one of the endpoints, to the center of point B. Okay. And then I am going to do a radius circle. And that radius circle is going to have a radius of equal to 3.7176. Enter. Okay. And then I'm going to do an extend under my trim, and I'm going to extend it to that radius so that it's the right length. So the radius of this circle, I did 3.7176, and then I extended that line of action that's perpendicular to link number 2 to that radius. Okay. Now I can get rid of that circle. I only needed that for construction purposes. And then now I'm going to put my arrowheads down and to the left, because this is rotating in a counterclockwise direction. Okay. And then I'm going to label that velocity of V. I'm just going to call it VB. Okay. And I might as well do a quick save. So I've got it on there. Okay. And I use and that's why the diagram is important, because now it ensures that that velocity of B is perpendicular to link number 2. And now I have this drawn to scale, pointing in the direction of rotation. And then I've got it labeled the velocity of B. So once I start creating my vector diagram, I'm now going to then just copy this vector down to it. Okay. It's in its right magnitude and its orientation or direction. Okay. Now the next one, I'm going to go to a new object later, is I am going to put in the velocity of C relative to B. So this again is going to be a line that is going to be perpendicular to link number 3, or the line connecting C and B. Okay. And I don't know if this is going up and to the left or down and to the right, so I'm just going to draw a line of action only. And then I'm going to copy this and I'm going to label this. This is the velocity of C relative to B. Okay. So again, just line of action, and then I'm probably going to have to trim and or extend when I do my vector diagram. And then my last one, make this one yellow. Okay, I'm actually going to move my D. So again, move your things around so that we're not overlapping. And now I am going to have a line of action from C horizontal through its center there. And this is going to be the velocity of C, and that's going to represent it. I don't have an arrowhead yet. I know it's going to go to the left, but I don't know where it's going to start and stop. So I don't want to put an arrowhead on at this point. We'll add that in our vector diagram. But these would be the magnitudes and or directions, kind of save often, of each one of our vectors in our relative velocity vector equation. So right now, any questions on those 3? Okay. So let's then draw our vector diagram. So what I'm going to do is we always have to have our vector equation identified. So this is going to be VC. So I copied VC over, is equal to the velocity of B plus vectorially the velocity of C relative to B. I have to make this longer. There we go. All right. So make sure you identify your equation. Now, just like we did for the vector equations that we looked at in chapter 3, we want to, kind of look at these 3 variables here and decide which one do we know the most about. If you recall, under here, we looked at each one of our variables. So where would we start? With C, B, or C relative to B? Where do we know the most? Nope. Do you have 2 check marks on C? You don't know magnitude for C. You only know its direction. Where do we have 2 check marks? At B, correct. The velocity of B. Velocity of B, we know magnitude. We know how long it is. We know it's going down and to the left, and we know it's perpendicular to link number 2. So that's why I do this right here. I identify, what do I know? Do I know magnitudes, directions? Do I know both? And once I know where I have the most information, that's going to be where I start my vector equation. I can't start with an unknown, right? Because I don't know the tip of that vector, where that's going to be. I couldn't start here because I know it's line of action, but I don't know where it ends. Okay. All right, so let's put in place the velocity of B. So as you know, I go back to my object line layer. I am going to, I don't know exactly how this is going to go. I forget. I'm going to put this in. Here's my origin. Okay. And my first vector, since I'm starting on the right-hand side with vector B, I am going to copy, because I'm going to leave it over here on my kinematic diagram, and on the tail, the endpoint of the tail is going to go to the intersection of my origin. Make sure you have an obvious origin identified, just like we've been doing. All of the labels that you see on here are required. Okay, so you have to put all your numbers and letters on your kinematic diagram, and then you're labeling each one of your vectors appropriately as well. So now I've got my velocity of B in place. I'm going to add vectorially C relative to B. So on the tip of VB, I am going to copy the line of action for C relative to B. Now I'm going to go just along the length here. I'm just going to go nearest, right about there. And then it's going to be to the end point, or the tip of the velocity of B. Okay, so that's overlapping. So here's where I would move this. If you don't move these things and make it easy to read, then unfortunately I'll have to take off points. Okay. So notice I added, in this case, the direction, if you would, that vector C relative to B would be on. Okay. So now that I've done everything that I can on the right-hand side of the equation here, I can't go any further, right? I'm going to cross the equal sign, which means I'm going to start back at my origin, and I am going to draw what I can for the velocity of C. I know the line of action of C, so I'm going to copy VC and its line, and I'm going to pick one of those endpoints, and that is going to be the direction of C. And I'm going to start it at the origin. Make sure that you have it starting at the origin. Now, I want to look for an intersection, right? So I can see that if I extend C relative to B up to VC, that is going to be an intersection point for me, okay? Now I'm going to move my velocity of C here. I'm going to trim the ends. So I'm going to trim off this part and this part, okay? So now I have my, they call it a vector polygon, but I basically have a triangle, right? I've got a triangle, and each one of the sides represents a vector. Now, don't leave this as is and just measure it. We need arrowheads, okay? So we're going to look back up at our vector diagram, and we're going to kind of look at what we're adding here. So I'm going to start on the right-hand side. Velocity of B. I'm going to add the velocity of C relative to B. So that means that the tail of C relative to B is going to be at the tip of VB, right? Adding vectorially. So that means that its tip is going to be at the intersection that we created with VC. So I'm going to go back to my object 3, and I'm going to go line here, representing its arrowhead, and line here. Okay. And then I'm going to put in the arrowhead for velocity of C. Now I'm going to cross the equal sign, which means that the velocity of C, it's all by itself on the left-hand side, and it's the first one. That means its tail is going to start at the origin, and its tip is going to go to the end of the last vector, which is out here. So I'm going to draw then. Oopsie. Oh, I have it on hatch. I don't want it on hatch. I want an object line. That's why. There we go. I was going to say, why isn't it in the same line? Okay. Bless you. Okay. So now I have my arrowhead, so I know exactly which way it's going. And we had thought it's going to go to the left. So this is confirming that, especially with the intersection that was created and the vector diagram. Now what I need to do is I need to measure, right? Get the magnitude. So I'm going to go back to my notes layer, and I am going to do a linear dimension. You could do aligned. If it's not along a horizontal or a vertical, you want to do an aligned, but this is horizontal, so for velocity of C. So I'm going to make sure I get the endpoint. So use your object snaps, endpoint to endpoint. And now we're going to measure that value. Okay. Now, this is where for your final answer, it is not 2.7255, is it? No. If you recall, we drew our velocity of B 100th of what the actual value was, right? We moved the decimal place 2 places to the left. So we basically divided by 100. So what we're going to do down here is your final answer that you put here with units needs to move the decimal place back to the right 2 places for its actual value. So if we go back over here, this is going to be 272.55 inches per second, right? You don't have to have the units here, but when you identify your final answer, and you have done things like move the decimal place so that you could get it at a reasonable scale, then you have to move the decimal place the opposite way for your final answer. So your final answer is not 2.7255, it's 272.55. So you want to fill that in with the units at the bottom of the page here. Did everybody get those same values as I did? No? Yep, then you have to go back and you have to fix it. Yeah, the very first place to start is going to be on your initial diagram. And if indeed you did screw something up along here and you use perpendiculars, then those numbers aren't going to be correct. For your assignment, I have the final answers in there for you. So if you, they're tested, they're right. So if you're like, mine aren't on there, but maybe this is a wrong answer. They're not. They're right answers in there. That means you want to go back, and the first place to start is right here. Okay. It's going to be your kinematic diagram and verify all of your numbers. Okay. So to hand in for this practice problem and the assignments. Okay. What you want to do is you want to kind of put this in a nice form. Now, if you can, I would move this so that you could get it all in one screenshot. Whoopsie, all in one screenshot, which I'm trying to do here. And no overlapping anything, if you would. Okay, so notice that I moved all my dimensions so that they wouldn't be in the way. And I also, you have to make sure that like this dimension is a little small here. So what I probably would do is, not that it has to be exactly the same as everything else, but I would modify it. And if you go on the Fit tab and you change this, I'm going to change this to 2. And I'm going to set as current and then close, and then it makes it a little bit bigger. If I can't see it, if it's grainy, if, you know, it's too small or it's not a right color that I can differentiate, I am not going to squint and try to figure it out. Your responsibility when you're handing these things in is to check the files before you upload them. For screenshots, because it's not vectors like this, like if I have the actual AutoCAD file, I can zoom in, I can continue to see the definition of the line. But when you guys take screenshots, okay, because I don't want the files, I want the screenshots. As I zoom in, it just gets grainier, okay? It does not get clearer. So if you are uploading it and you're noticing that your file is grainy, then it's gonna be that for me too. And if I can't read it, it's a 0. I'm sorry. Okay. So look at those files before you upload those. So you're going to take a screenshot of your kinematic diagram with all the labels, with the vector, like the VB, I don't know how to say that, the VB, the VC relative to B, and the VC on the vector or on the kinematic diagram. And then you're going to copy those. And I want to see your vector diagram. I want to see the vector diagram equation, all the labels here, as well as your final answer. Now, you might say, don't I need to determine the magnitude of the velocity of C relative to B? The answer is no, unless the problem asks you to do that. The final answer for this problem was, what is the velocity of the slider? Okay, how fast is that slider going? This is the answer for that. The slider is point C, velocity of C, which is on the slider, and it is going horizontally to the left at 272.55 inches per second. That's what it wanted. We needed VC relative to B to get there to find that intersection, but it's not asking us for a magnitude. If it would say, what is the relative velocity of link number 3? Well, now you have to measure it. I don't think any of the problems ask that, but we need it to get our intersection. Does that make sense to everybody? So this would be what you want to take a screenshot of, what you see exactly here, and you do this for your practice problem. So not only are you filling in the values in the handout for the practice problems here, like we did early, you know, this part here underneath. Okay, so we need this filled in, okay? But you also need the screenshot of your values here, okay? And this is what you would do also for your homework problems. Okay. So what I'm going to do right now is, this is a good place to just take a little bit of a break. We have another example that we're going to be going over when we come back. And then we'll resume. So I am going to pause our recording here. Okay, so the next problem that we're going to be looking at is it's actually the last problem on the final page 10 in our handout. And this is going to be problem 627. It is not a homework problem. I took it off the homework because we're doing it here as a practice problem. So, so on page 163, problem 627, which is right down here, I'll zoom in. We want to start by drawing the kinematic diagram for this, okay? We'll go like this. And we'll read the problem statement after we kind of get things in order here. So go ahead and draw the kinematic diagram for this problem. So problem 627 on page 163. This is a metric. So so you want to pull up or scale so that you can have it about the right size for millimeters. What I'm going to do in the background here is get mine done as well. I'm going to open. I already did this one. Yeah. So I am just going to. Okay, so once you have your kinematic diagram in place, so I'm just going to briefly go back to AutoCAD here. So here is mine. Again, make sure that, when you kind of put your final touches on and you have your labels, when you do your screenshots, make sure that we can see, or I can see, each one of your link numbers, your joint letters, okay? So I'm going to go back over here underneath. So this is just a sketch of that kinematic diagram. So we can kind of, sketch before we put in AutoCAD. So we drew our kinematic diagram. We have everything in place. Now the problem. Let's look back at the problem. We didn't look specifically at what it's looking for. So let's find out exactly what it's looking for this mechanism. So it says the device in this figure is a sloshing bath used to wash vegetable produce. For the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath as the crank is driven counterclockwise at 100 RPMs. So it's identifying the crank down here for us. So this is going counterclockwise in this direction at 100 RPMs. And we want to find out, okay, this is going to oscillate, all right, back and forth. We want to know what is that angular velocity. So that means that it's going to be W of the link associated with the bath, okay? So if you look on your kinematic diagram, we want to know what W4 is here. Okay, we want to know what W4 is, the angular velocity, not the straight line velocity. It's not V, it's W. Okay, now to calculate W, we know that our base equation, okay, is W is equal to V over R, right? Or V is equal to WR. This is just a rearrangement of that. Now, if we want to find W4, so we're going to put 4 underneath here, right? That's what we're ultimately wanting to find. Now we want to fill in what is the velocity and the radius that we're going to use here, okay? So W4 is this link right here. So you'll notice that D is the point that is connected on that link to the frame. That is not moving in a straight line velocity, is it? So what other point C is on that link, right? So this is going to be the velocity of C divided by the radius to its center of rotation. So C can only travel along that arc, and its center of rotation is back at D. So the length of this member, or this link, which is 770 or 720 millimeters, is going to be our value. So that's going to be the radius or the distance of link number 4. Okay, does that make sense to everybody? Now we look. Okay, if we want to know what that angular velocity is of link number 4, do we know the velocity of C? Do we know its magnitude? No. We know business over here. This is our input, right? Input. Okay. This over here is our output. Okay. So we don't know about our output. That's what we're trying to find, right? So we don't know the velocity of C's magnitude, but do we know anything about its direction? Yeah, we do. Draw in what you believe to be the direction for the velocity of C. So velocity C is going to be perpendicular to the link that it rotates around its center of rotation. Velocity of C is going to be going perpendicular to that link. And this is going to be going, if this is rotating this way at this moment in time, this is going to also be going counterclockwise. Now, I don't know how long velocity of C is, but I know it's going to be going up and to the left. Okay. So if you want to kind of extend that and just kind of make it, it's going to be along that line, perpendicular to link number 4. Okay. Now, because link number 4 is over here and the driver for it is over here, we're going to use that velocity, or I'm sorry, the relative velocity equation to solve for it. So velocity of C is considered an unknown. So velocity of C is going to be equal to velocity of a known plus vectorially the velocity of C relative to the known. So we don't know what the known is yet, but we might have a good idea. If we go back up here, where we know the most information is at our input, right? We know that that link number 2 is going counterclockwise at 100 RPMs. You'll notice on the end of link number 2 is velocity of B, right? So I should be able to calculate that magnitude. All right, I should be able to. So our known, just like it was in the last one, is going to be the velocity of B. Okay, so remember this is unknown, known, and this is going to be unknown relative to known. It's kind of like its generic form, if you would, and then we fill in the letters for the things that we know and don't know. So if we look back at our diagram, draw in what you believe to be the direction of the velocity, straight line velocity of B, VB. You should have it going, might even be close to that link number 3, but it's going to be going up and to the left, perpendicular to link number 2, right? Now, magnitude-wise, we should be able to figure this out because we know that the velocity is equal to angular velocity times its radius to its center of rotation. When we're solving for velocity, just again, rearranging this equation to here. So if I'm looking for the velocity of B, its magnitude, which link, angular velocity of which link am I going to use? What link is velocity of B on? Ben, link number 2, exactly. So we're going to put a 2 there. And then the distance that it is away from its center of rotation is also going to be the length of link number 2, or the radius, right? To that point. Okay. So let's calculate the velocity of B. Go ahead. I'm going to give you a minute to fill in your values for W2 and R2. Now, as we look at this equation, our W2, we're reminded that we have to use radians per second in and out of this equation, okay? So we're given W2, its angular velocity of link number 2, or that crank, is 100 RPMs. We cannot put that directly in. We need to convert that to radians per second first. So whether you do that on the side, or if you do it inside the problem, like I normally do, you can do it either way. So I'm gonna add it right in here. So my W2 value that I'm given is 100 revolutions per minute. Okay. I'm going to convert that to radians per second. So 1 revolution is equal to 2 pi radians on top. Revolutions cancel. And then I've got 1 minute is equal to 60 seconds. And here again, by doing it this way, multiplying across the top, dividing by the bottom, making sure that you have the right units left over that aren't canceled out. You know that you have it set up correctly. You don't have to try to remember, do I multiply, do I divide? Okay. Now that's going to be our W2 converted to radians per second right in the problem. Now I'm simply going to multiply that by the length of link number 2. So in the problem, that is 80 millimeters. Okay. So now I'm going to multiply across the top, 100 times 2 times pi, divided by 60 times 80. Okay. And you should get a magnitude of about 837.76 as your value. That's what you got, Ben? Okay, excellent. Ben in the back as well. Aaron got that? Good. Units. What are my units here? Millimeters per second. Exactly. Millimeters per second. So this right here, my friends, is magnitude. Okay, that's the magnitude of the velocity of B. Okay. Now, let's peek down here. We already knew that we needed to use our relative velocity equation. So let's check to see what we know and what we don't know. So again, looking at each one of these vectors in terms of magnitude and direction. So do we know the magnitude of the velocity of C? Velocity of C is right there. No. Actually, that's something we're going to find, right? We're going to find that. So we're going to put a circle there. Do we know the direction of velocity of C? Yeah, we do, right? And we're going to use our CAD diagram to help us with that. So we do know direction. Then we're going to go to velocity of B. Do we know magnitude of velocity of B? Yeah, we do. Step number 2, we got it. And do we know direction? Yes, right? From our kinematic diagram. So this one is fully defined, magnitude and direction for the velocity of B. That's why we call it the known value. And then C relative to B, we didn't do this one yet. So C relative to B, if we go back up here, remember the direction or the line of action of C relative to B is going to be on the line connecting C and B. So it is going to be perpendicular to link number 3. We just don't know which way it's going yet, but that's going to be the direction of the velocity of C relative to B. So down here, we don't know its magnitude. Just like we did on the first one, we'll find the intersection, but we do know direction. So here again, we're in good shape because we know I'm sorry, we only have 2 unknowns and they are separated by the equal sign. If you end up having more than 2 unknowns in this equation at any time, you're going to find when you try to do your vector equation, you're not going to know what to do. Okay. So if you forget this step, you got to find something. One of those values, one of those magnitudes is going to be able to be solvable, if you would. Okay. So now we're ready to draw our vector diagram. All right. So I'm going to go back to AutoCAD. Okay. And the first thing that we're going to do, and I kind of did this over here, so I will move. I'm just going to do the lines for you guys. Okay. I'm going to leave my variables there because I am. So I just want to see, I did. Okay, great. So I'm going to use green here. You can use whatever colors you want. But I'm now going to start with my velocity of B. So this is putting it on the actual kinematic diagram and using the kinematic diagram to get my directions. So I'm going to draw a random line, okay? And I'm going to start it out here. And I just want to be, and I'm going to zoom in. I want to be perpendicular. So I'm doing shift right mouse button, and I'm going to be perpendicular to this line right here. Okay. Now, if it goes off, that's okay. It'll still make it perpendicular, even if you end up off of the actual link. Then all you want to do is you want to move then this line that you just created perpendicular so that the end point, Where's my endpoint? There it is. My endpoint is going to be at point B. Okay. Now I drew this a random length. Now to get it to the actual length, I am now going to do a circle with a radius. Center point is going to be at point B. And I am going to make that radius a length of the magnitude of B, 837.76. And then depending on the scale that you're using, you can adjust that if needed. And then I'm going to extend. So underneath trim is extend. If you use that, I'm going to extend that to the radius. And now I have my velocity of B at the right magnitude. I'm going to delete the circle because I don't need that anymore. Just needed it for construction. And now I'm going to put my arrowhead for the velocity of B. Okay. I'm going to go to the velocity of C relative to B. So I'm going to change my color here. And I'm just going to make a line, random start point, and then perpendicular to link number 3. And that is going to be my velocity vector for C relative to B. And then lastly, I'm going to change my color one more time. I'm going to do a line out in space, perpendicular to link number 4. And then I'm going to move its endpoint. Make sure you grab the endpoint. If it looks close, remember, just be really careful. And then endpoint here. There we go. And that's at point C. And then we'll do the vector diagram in just a little bit. I just have that over there from a previous problem that I did, but it's just, we'll go through the start to finish. So does everybody have their vector, either magnitudes, velocity of B here, both magnitude and direction, as well as then the directions of C relative to B and C? Okay. All right, so now we're going to use these lines to actually create the vector diagram. So I'm gonna delete underneath here. I'm gonna get rid of this one. Okay, so now underneath here, this is my vector diagram. So just duplicating what we have in the problem earlier, the velocity of C equal to the velocity of B relative to C relative to B, or plus vectorially C relative to B. If we go underneath here, okay, we want to start on either the left or the right side of the equal sign where we know the most. So we have fully defined at velocity B. That's going to be the first vector that we're going to start with. So going back over, I'm going to start by placing my origin. And it looks like it's going to be down here-ish. So I'm going to do a line. Okay. Now, the tail of my first vector is going to start at my origin. The first vector that I'm going to put here is going to be the velocity of B. So I'm going to copy. And I do want to see your vectors and line of actions on the actual kinematic diagram. So do a copy when you move your vectors. So I'm going to go from endpoints to intersection. See? There we go. Make sure that the tail of the velocity of B starts at the origin. And then your tip is going to be, in this case, up and to the left. Now, on the endpoint of velocity of B, on the tip of B, I'm going to place the tail, if you would, of the velocity of C relative to B. Now, we don't know if it's going up and to the left or down and to the right, okay? So what we're going to do is we're going to copy C relative to B, and I'm just going to go along the length here. So I use the nearest object snaps because I don't know if I'm going to be going down or up. Make sure that I'm at the endpoint. I am. Okay. So that's C relative to B. Adding its line of action to the endpoint. Now that's as far as I can go on the right-hand side, right? Because I don't have an endpoint. So now I'm going to cross the equal sign, and I'm going to start with vector VC. So if I look at VC, that's up here. That's my yellow one. So I'm going to copy that. I'm going to select both of those. I'm going to start with the end point of VC, whether it's one or the other, doesn't really make a difference. And I'm going to put that at my origin, okay? The intersection of my origin. And now I'm going to look for an intersection between C relative to B and C. And you can kind of see it there, right? So what I'm going to do is I'm going to make a line out here, because when you extend lines, if there's nothing out there to extend to, it's not going to go. So I'm just going to put a random line out here that I can extend my C to and my C relative to B to. So I'm going to do the extend function up and up. I guess that might be far enough. And then I'm going to extend my next one. Here we go. Okay. So now that's the intersection. So now what I can do is I can trim away the things that I don't need. So I'm going to go back underneath to trim. I'm going to get rid of that, get rid of that. And then I can just delete the leftover stuff. Okay. So let's focus down here now. I'm going to move my C relative to B, oopsie. C relative to B to the outside here. And then I'm going to add my arrowheads, okay? Now, the velocity of B plus vectorially C relative to B. So that means on the tip of B, I have the tail of C relative to B. So that means its tip is going to be up and to the right. So I'm going to change back to that line type, and my arrowhead then is going to be going up and to the right for C relative to B. You have to put the arrowheads on every vector, even if you're not, if you would, calculating, because you're identifying this as a vector. A vector is not just a line, it's a line with an arrowhead. Okay, so even if we're not going to grab the magnitude of that, you have to put the arrowheads on each one. Make sense? Don't forget that. All right, and then now VC is on the other side of the equal sign, so that means its tail started at the origin, and its tip is going to be going to the tip of the last vector. So I'm going to change this to my yellow line, and I'll go something like that. I'll make it a little bit longer because this one is my final answer, right? Okay. So that means that up on link C, this is going up and to the left, okay? Up and to the left. All right. Now, magnitude. I'm going to change to my notes layer, and I am going to do an aligned dimension. Make sure you grab endpoints. And I got 815.1723. Now, this is a one-to-one scale for me. Remember, the length of my links were like 800, 700, that kind of thing. So if you need to go to the dimension style manager, go to modify. The dimension I use is I scaled it up 200 times, it looks like, just to get the text large enough. I'd actually go with even a little bit bigger. I'm going to go 250. See how that changes it. Set as current close. Okay. Yeah, that makes it a little bit bigger. Okay. So if that helps as far as dimension scale, it's going to be super tiny when you first put the dimension in, but if you use something around 200, 250, that should be large enough for you to see the value. Okay. Now, we're not done. We're not done, because let's go back to the problem. Even though on the last problem, we had a slider crank mechanism and we stopped at the velocity of C, right? Because that was the slider moving horizontally. This is a straight line velocity. Let's go back to our problem. And if you recall, it wants to know what the angular velocity is of link number 4. Link number 4 is not a slider this time. It is pivoting, or it's oscillating around its fixed center right here. So it's kind of going like this, back and forth, okay? So what we did was we calculated this point out here, the straight line velocity of C. We did not calculate an angular velocity yet. So that is not your final answer, but we need C to calculate W4, or the angular velocity of 4. So if we go down here, or I'm sorry, up here, this, we just calculated the magnitude. This is the equation we're going to use for W4. So let's go down. Oopsie. Why that's doing that? We know that W4 is going to be equal to velocity of C divided by the radius of link number 4. So we just calculated our straight line velocity of point C. And that was, let's go back to AutoCAD and get our number. That was 815.17, and that's millimeters per second. Millimeters per second. How do I know it was millimeters per second? Well, if I go back underneath here, remember for velocity of B, it was millimeters per second. So anything in that velocity triangle will have the same units. Okay. And then my radius of link number 4, that goes back to the original problem. The length of that was 720 millimeters. You have to put your units in every phase of the problem, and you have to cancel and or combine. So you'll notice here that our millimeters cancel out. Okay. So let's get our number first, and then we'll talk about units. Okay, so let me see here. W4 calculator. So the value I get, which I believe I know it's correct, 1.132 is my value, right? Now, you're going to notice that top to bottom are millimeters canceled out, right? Millimeters canceled out. So we have, if you would, nothing per second. Or do we have something else? What do we have actually? Nothing per second. We actually have what? What magically appears? Radians. So we're at radians per second. Remember, in and out of this equation, this is the outside of it. I'm calculating for a W. I am going to get radians per second. If you don't, you didn't set it up correctly. Okay, this is why we need to know our units and what we're expecting, because that way, when we check to see what the final results that we got were, we can compare the units that we got to what we're expecting. Okay, in this case, we're expecting that. Okay. All right, am I done now? Because I got my W4. Ben is saying no. What do I need to do? Back row, Ben. You guys are right next to each other even. Yes, we need to change it to RPMs, or revolutions per minute, right? Yep, so go ahead and do that, okay? Go ahead and do that and see what you get. I'm getting 10.81. Make sure you can get that on your calculator, okay? Make sure that you get it with what you have written out here, because that lets you know that, again, that you have it set up correctly. Notice that the cancellations leave me with revolutions per minute. My value is 10.81, and you can put RPMs after it. You don't have to put rev per minute top bottom for the final answer. You do need to, kind of show it expanded when needed and such. Now, some students will ask, could I show this work, like anything that we did handwritten, okay, in the CAD file? Yes, you can. You can. Or you can show the work separate like we have here. Now, for the practice problems, you would have this filled in, okay? And then you are going to do the screenshot of your vector diagram and your kinematic diagram with the directions and the labels of your different velocities. I want to see this. This is important to me because it tells me then that you understand and know what you're perpendicular to and what the directions are going to be. Okay, so once you put these in place on your kinematic diagram, then you copy them for your velocity. So don't move them, copy them. So I can see them in both places. Does that make sense? That's of value to me. That lets me know you know where things are coming from. So these two diagrams, I know I have this one over here, but I want to see it with the added directions of your velocities and then the vector equation. So if you want to get this on one screenshot or two, that's totally fine, but you would add that to the practice problems here. Okay. All right, questions? Okay, so let's take a peek underneath at our practice problems. So we did 2 relative velocity problems today, graphical relative velocity. These are going to be the last problems. I think there's 4 that you're going to be doing for your homework. Okay. We did one where it was a crank mechanism or a crank with an oscillating out here. And then we also did one where it was a crank slider mechanism. Okay. Those are the 2 that you're going to encounter in your homework as well. All right. So you have full problems of 1 of each. Okay. So, so that concludes, if you would, the practice problems that I was intending to go over to set you up for your assignment. All right. So I'm going to stop the lecture here. Are there any questions, first of all, on the handout practice problems right now? Okay, so then what I'm going to do is I'm going to stop the recording here, and then the next recording that I'm going to do is going to be dedicated to the practice problems and the assignment and what you're handing in for those, okay, to kind of give you an overview.